Welcome to Lesson 8 of Stochastic Processes. In this lesson, we're going to continue the classification of Markov chains. We're going to talk about positive and null recurrence, periodicity, and stationary distributions. We have a subdivision of the recurrent state. As you recall, the recurrent state is one where the Markov chain returns with probability 1 to the given state. But the expected return time may still be infinite. So when the state is recurrent, but the expected return time is infinite, the state is said to be null recurrent. And when the expected return time is finite, the state is said to be positive recurrent. So an important comment here, this distinction is not technicality. It decides whether a chain has a stationary distribution at all. So a stationary distribution is the probabilities in the long term of being in different states. So we need to have this positive recurrent in order to compute stationary distributions. Then there's a shorthand. We'll be writing this here, expected return time to state I, given that you've started in state I. I've used that up here already. Then I have an example here. The symmetric random walk, that's in one dimensions where you have probability 1/2 going left or right. It returns to the starting point with certainty, probability 1, yet the expected time to do so is infinite. So it's certain return, but with no finite average waiting time. I have a couple of theorems here. Again, these are from my book, which I've referenced a couple of times in previous lessons. If two states, I and J, are recurrent and communicate, and I is positive recurrent, then J is positive recurrent. The states of a recurrent communication class are either all positive recurrent or all null recurrent. Okay, so this is sort of a fine-tuning of the theorems we had towards the end of the last lesson. Then we have this related theorem. The states in a communication class are either all positive recurrent, all null recurrent, or all transient. And you almost don't need this second sentence, but I'll give it here. In an irreducible Markov chain, so in other words, when you have one communication class, the states are all positive recurrent, all null recurrent, or all transient. Then I have a couple of notes here. So the three-way classification travels across communication class exactly as recurrence did. For an irreducible chain, one calculation classifies the entire chain. Theorem 24 simply combines theorem 21 from the previous lesson with theorem 23 from above here. Periodicity, what is that? You probably have an idea just from the term. A chain can return faithfully, yet only at multiples of some fixed number. So that's sort of the idea of periodicity. And we had an example of that was the one-dimensional random walk, where all the return times to a state were multiples of 2, an even number of return times. So the period was 2 in that case. The formal definition is the period of a state is the greatest common divisor of its return times, written more formally like this. And then we say if the period is greater than 1, the state is periodic, and if the period equals 1, then the state is aperiodic. A self loop at a state x forces dx equal 1, the GCD of all the return times to be 1, since the return in one step is possible. That's what I've written here in notation. If the probability of returning back to the state in one step is greater than 0, then the d of x equals 1, and the state is aperiodic. Okay, so let's look at some examples. I have an example here, and I call it a chain of period 3, but I'll explain that in a second. Let's look at the state 1 first, and see if we can figure out the greatest common divisor of the different return times. So we could go 1 to 2, 2 to 4, and back. So that's 3 steps this way. And of course, it can keep doing that. It can make it 6 and 9 and so on. But there's another way. You can do from 1 to 2, 2 to 4. So it's 1, 2, and 3, 4, 5, 6. So you could also do that. That's a longer one, but that's still a multiple of 3. It's 6. So the GCD of all those numbers is 3. So state 1 has period 3. And then we have a theorem on the next slide that says that every other state in this irreducible chain has a period of 3. We might want to look at another one just to convince ourselves. Guess we could look at 3. So that's let's see, 1, 3 to 2, 4, 3. So that would be 3, right? This way here. And then you could go from here to here. That's 1, 2, 3, 4, 5, 6. So again, you have multiples of 3 getting you back to state 3. So this also has period 3. I won't go through the details, but 2 and 4 also have period 3. And we're going to have a theorem that'll give us that result. So we don't need to check every last state. We could just check 1 in an irreducible Markov chain or a communication class. Periodicity is a class property. That's what I mentioned on the last slide. And we have the theorem I alluded to. If x and y are in the same communication class, then d of x equals d of y. Remember, d of x is the greatest common divisor of all the return times back to x. So we have a proof here, and I just want to mention to you from a result from number theory that we'll use a little bit further down. If you have, say, x dividing a and b, and we're talking all about integers here, then x divides a plus b and x divides a minus b. So, for example, if x is 3, and it'll divide 9 and 27, and then it also divides the sum. 3 divides 36, and the difference, which is 18, is also divisible by x. That's true in general, so we'll need to use that in here. So since x and y communicate, there's integers k and m such that there's a path from x to y in k steps. It's probability greater than 0. And also from y to x in m steps was probability greater than 0. So going x to y in k steps and back in m steps is one way of returning to x. That's what I'm showing here. So these two are both greater than 0. But this is only one way of going from returning from x back to x in k plus m steps. So in general, this probability is bigger because there's more possibilities here. So what this implies is that k plus m is a multiple of the GCD of the return times to x. So in other words, x plus m equals some constant times dx. And now from here, so in other words, dx divides k plus m. Maybe it's a more direct way of saying it. So we insert a loop y into this here, y back to y, I should say, of length L. So any loop that gets us back to y, starting from y, pick this arbitrarily as long as it goes from y to y. We insert that in here. So this is, all three of these are greater than 0. And this is a specific path, x to y to y, L times, and L steps, and then y to x and m steps. But this is more general. There's more ways of going from x back to x and k plus L plus m steps. So using the same argument here, k plus L plus m is also a multiple of dx. So L must be 2. And that's the number theory result I mentioned. The difference of these two is L. So L is a multiple of d of x. So in other words, L equals some constant times the d of x. Since L was arbitrary, d of x divides every return time of L, of y. We just picked one, L here, but d of x divides all of those. So that means that d of x is less than or equal to d of y. And then we can just go back through the same set of steps, reverse the roles of x and y, and show that the d of y is less than or equal to d of x. And then, of course, these two things together imply that the d of x equals d of y, which is what we wanted to prove. I have an example of an aperiodic chain on this slide. The chain is irreducible. I'll leave it for you to check, but it's basically you can get from any state to any other state in this Markov chain. So we know since it's irreducible, we know we just need to check the GCD of all the return times for any one of these states, and it'll be the same for the other ones. So we're going to pick 4, and you can get from 4 back to 4, you can go 4, 3, 2, 1, or 4, 1, 2, 4. So both of those are three steps, and you can, of course, go once this way, once that way, and cycle, but they're all going to be multiples of 3. And then the other way is longer. You go 4, 3, 5, 6, 7, 8, 3, 2, and 4. That's 8. So any loop that gets back to 4 is some combination of the loops of order 3 and the loops of order 8. And so since 3 and 8 don't have a common divisor, the GCD is 1, other than 1. And that means the D4 for this state is 1. And so state 4 is aperiodic. And by theorem 25, so is every other state in this chain here. Okay, so you may want to try another state just to convince yourself that you're going to get the same GCD of 1, just as a test. If we add one more state, this state number 7 here, to the Markov chain from the previous slide, we actually get a periodic Markov chain. So let's have a look at that. Now we can consider any of the states, but let's look at 1. So we can go from 1 to 2 to 4 to 1. That's this first one here, that's 3. Then we can do 1, 2, 4, and then we go out to 3, 2, 4, and 1, so that's 6. And we can do any combinations of those two that I just mentioned, but you're going to get something that's divisible by 3. And then we have the longer path now that we've added 7 in here. So I've written it out. Let's see if we can reproduce it. It's 1 to 2 to 4, 3, and then you kind of, in this loop here, 5, 6, 7, 8, 9, 3, 2, 4, and 1. So that's 12. So you can take any combination of these basic paths that loop back to our state 1, and they're all divisible by 3. So in this case, the GCD of the return times back to state 1 is 3. And so not only is one of the period 3, but all these other states are also of period 3. So the GCD of their return times is 3 in every case. You may want to check a few more just to see that. In some cases, a Markov chain settles down in the sense that the long-term proportion of time it spends in each state stabilizes. We let pi sub j be the long-term proportion of time the chain spends in state j, and we actually define it more formally down here. And you have the sum from k equals 1 to n of the indicator function of x sub k equaling j. We divide by n and take the limit as n goes to infinity. This is equivalent to this here, and we know how to compute these probabilities. That's the probability of going from I to j in k steps. We sum that from I equals 1 to n. Presumably there's an n in that formula. We divide by n and take the limit as n goes to infinity, and that'll give us the proportion of time that the Markov chain is in state j. It turns out that this is not dependent on I, and we'll see that on the next slide. Transient and null recurrent states both have 0. As you might suspect, you don't average any time at all in those states, which is why positive recurrence is assumed for these computations. Okay, so let's look at an easier way of doing this, and then in the slide after that we'll do an example. Okay, so if a chain is irreducible and positive recurrent, then independent of the initial state, the long-term proportion of time in state j is the reciprocal of the expected return time. So it's this here. So that's one theorem. Then we have, I think, a more useful theorem, at least for the example we're going to see on the next slide. For an irreducible positive recurrent chain with state space S, the long-term proportions solve these equations, which in matrix form are these equations here. So pi equals pi times the transition matrix, and then pi, this is the matrix with all ones in it. Not the matrix, but the column vector with all ones in it. So it's basically the sum of the pi sub i's. That's what this is here. This is equivalent to this, and then this is equivalent to this. So let's see how to use these on one of our previous examples. We'll do that on the next slide. So here's our example that we saw this earlier, and I just wrote this Markov chain in terms of the transition matrix. You notice you can go from state 1 to state 2, probability 1, from 2 to 4, probability 1, from 3 to 2, probability 1, and then state 4 could go to either 1 or 3 with probability 1/2. So this is our matrix T, and then if we multiply pi times, or pi equals pi times T, if we do that, where pi is just a row vector with components pi sub 1, pi sub 2, pi sub 3, and pi sub 4. So if you do this multiplication, you get these 4 equations. And then this is the bold one here. This is the column vector with ones, as I mentioned on the previous slide. That gives you the sum. Then you notice pi sub 1 and pi sub 3 equal the same thing. So they're equal. And we can plug that in to this equation, and we get pi sub 2 equals 2 times pi sub 1. So, and pi sub 4 equals pi sub 2. So we have pi sub 1, then 2 times pi sub 1, and then pi sub 1 again, and then this is 2 times pi sub 1. So we get 6 pi sub 1 equals 1. We can solve for pi sub 1, and we get pi sub 1 equals pi sub 3 equals 1/6. And then the other two are just 2 times this. We get 1/3. And so the stationary or long run proportions are 1/6, 1/3, 1/6, and 1/3. That means in the long run, if you let this Markov chain run, with these probabilities, you're going to be in state 1 a sixth of the time, state 2 1/3 of the time, state 3 1/6 of the time, and state 4 1/3 of the time. So that's our example, and that's the end of the technical part of our lesson. I have one more slide that summarizes some points from this lesson and then gives you a little bit of a preview for the lesson after this. I have a summary of our lesson on the right. So recurrent has two subclassifications: positive recurrent, where the return time is finite, and then null recurrent, where the return time is infinite. All three labels, positive recurrent, null recurrent, and transient, apply to a communication class. The period d of x equals a GCD of the return time. We define that. A self loop forces d to equal 1. Two coprime loops force aperiodicity. So we saw that we had an example where we had one loop was 3, a period of 3, and another loop in the same communication class was of size 8, and so the GCD turned out to be 1. Then we have the formula a couple slides back, where pi sub j is 1 over the expected return time going from j to j for irreducible positive recurrent chains. And then we just saw these equations here where we can solve for the components of pi and then get the long-term proportions of being in each of the states of a Markov chain. Okay, so that was this lesson. Next lesson, part 9, we talk about continuous time. So far, everything has been discrete. We talked about steps, 1 step, 2 steps, so on. So you can also have continuous time chains, chains that can change state at any moment, holding times, and why the exponential distribution is forced on us. So we'll talk about holding times and counting processes and the axioms they satisfy. And then this sets the groundwork for the Poisson process in part 10. And then there's also a part 11 and 12 that I haven't done yet, but that's my plan. So we're getting there. We have 9, 10, 11, 12. So we have 4 more lessons left.